Okay, so in this video clip, we're going to take a look at the Hull White model again, 2004, and we demonstrate that when you introduce the Boyle-Lau specification, the model is optimized, converges more quickly, and you remove many of the issues around sawtooth path convergence. Okay, so taking the parameter values as given here, if we change the step size going from 1,000, going from 500 up to 5,000, we can see a smooth convergence of Hull White Boyle. In the original Hull White model, without um, any optimization, you typically see sawtooth pattern of convergence, and that's a bit disconcerting because it's hard to find true. Now, the values for true here we have in our table were supplied by Svi. So we could develop the Hull White Boyle mode so it converged to true. Um, Also, in terms of the optimal code or optimized code we're using here, we make use of the NumPy library. That's a bit fast, or a little bit faster than the math library, and not too bad compared to Cython or C++ in terms of speed and in terms of performance. And we can verify here when we run this code for the parameter values that we have included in the code snippet here, when we compare directly against the actual table that we've published here, that at the 5,000 step using these parameter values that are consistent with the ones we've stated here in the table, the value of the option 278535 we can replicate. And if we change the step size to a lower step size, let's go back, let's say go back to 500, we can verify the output figure, the 2786 is the same as here. If we change the multiple from 1.5 to 2, keeping all the other parameters consistent and run that again, we can observe that the output, the model, the 3498 is true. We can verify that the Hull White Boyle model. And also, if we increase the step size from 500 up to 5,000 and run the model again, the value of the option is 3499, which again is close to the true value supplied by Svi. Okay, other optimizations included in the tree is we strip off the early exercise. So once the barrier touches the lattice, the early exercise triggers, and we don't need these nodes become redundant. We can leave out and we strip off. And also in the code, the zero region, which is common in call options, binomial call options, a section of the tree is typically redundant because it's just zero value. So even though we might calculate these values, they have no bearing on the backward recursion process and no effect here on this specific node, right? At the apex, right? So when we estimate the apex node return opt 0, right? This one, no effect if these are 0 here. So they can be sheared off. Okay, now when we run the code, it executes, no issues, and we get our output. And we can do a quick time check just to verify that it's executing quickly. With 5,000 steps, it's been executed on average in 248 milliseconds. That's quite good. Um, Other things we would like to investigate perhaps is what happens when we change the stock price and keep all the other parameters constant. So we could take the parameters above as given and just change the stock price based on the NumPy command here, right? That outputs 10, 20, 30, 40, 50, all the way up to 160. So if we execute that and then graph it using the matplotlib library, we can trace out the different stock prices on the horizontal axis relative to the value of the option on the vertical axis. And again, just to verify that the results, the ESO see what the original prices are. So the stock prices, if we take this variable here or array, what actually is that stock prices and execute, we can compare that against what's in our code. So it's 10, given that it's 16, 17, we could go 16, might make more sense. You could see for 16 steps in the tree, it's a 16 intervals of it becomes intervals of 10. So if we go from 10 to 116, and we're performing 16 estimations at uniform intervals, then the stock price is being entered in as 10, 20, 30, 40, 50, 60, all the way up to the 160, right? And if we run the pricing on the option, then we get that output from the parabola is takes on the usual parabola. If we wanted to maybe go a little bit higher, 190, we could put in here 119, and maybe we get more shape in our parabola over a broader range of values. Okay, so it goes up to 190. Okay, and if then we were to uh, observe the effect of changing, in this instance, the volatility, we could take the parameter values as before, set them out. Notice that in the list here, we don't include sigma. And then to introduce sigma going from 10, 20, 30, 40, 50, 60, 70%, or zero point 0.1, zero point 0.2 up to 0.7, then we can use the linspace command and then graph the output from our uh, running the model as 6 times. And we observe as we increase the volatility, the value of the option would appear to go up. Okay. And then finally here, we could also just take, if we wanted to very specifically go 1.1, 1.2, 1.3 for the multiples. If we want to investigate the effect of changing the multiples, right, we could um, specifically state, so I'm not using NP lin space and go from particular set out as before. This is this is imposing 1.1, 1.2, 1.3. And then in our ESO, run the model for multiple. So we enter here multiple in multiples. So these values are populated each time we run through the estimation so that we produce 1, 2, 3, 4, 5, 6 estimations of the option. Then graphing that, we produce this graph here. Okay, so uh, keeping the code in Python and fast executing, not traversing between C++ or Cython. NumPy doesn't do a bad job, and the code here we verified is consistent with true. Um, so if we want to do further parameter sensitivities, we could very simply follow the approach we have here by just changing the relevant variable and then inputting that into, so for the stock prices, we say stock, and then for stock in stock prices. So you could see we using linspace, we can generate 10, 20, 30, 40, all the way to 190. And then we input our values as before, and then we amend our code, our function, so that it is for stock in stock prices. And then we can generate the graph using the stock prices, the varying stock prices, and the output from the model itself for the employee stock options. Okay, let's leave that there for parameter sensitivity.